So in today's lecture, I'm going to start our discussion on optoelectronic detectors, or you can say optical transducers. So some common optical transducers and their working principle is going to be discussed in this one or two lectures covering the optical detectors. So the optical transducers can be also useful for different applications, such as uh, primarily if you want to measure intensity of light, then that can be measured, or the property of optical transducers can be even used to measure the distance between an object, or in detecting an object, or uh, controlling for different controlling operations, such as controlling the turning on and automatic turning on and off of street lights, and these sort of applications actually, or even the pulse oximeters, which are popular these days due to the COVID. So those are also based on mostly optical sensors. So the first type of optical transducers that I'm going to introduce is the photoemissive cells, or phototubes. So these photoemissive cells can be basically of three types mentioned over here. That is the vacuum type photocell, gas filled photocell, or photomultiplier tube. So first of all, I will start with the operation of the vacuum type photocell, and later on I'm going to proceed with the gas filled photocell and the photomultiplier tube. What are the modifications in the later designs, and what are the advantages or disadvantages? So for vacuum type photocell, normally these are also called phototubes. So let me discuss about the construction first. So the construction is quite simple. There is a cathode terminal and an anode terminal, which are enclosed in a closed chamber, actually evacuated chamber. So the cathode is normally in a concave shape, or a curved sheet of metal, and in the concave surface of that curved sheet, some photosensitive or photoemissive material is coated, and there is a separation between the anode and the cathode. So anode is a conductive bar. So whenever there is some incident light or incident radiation on the concave surface of the cathode, if the energy of the incident light is sufficient to uh, ionize that photoemissive material, then that material will uh, uh, eject some electrons, and those electrons are going to be collected by the anode. And in this process, when this particular device is connected in a circuit, this will eventually result in a flow of current. So from the measurement of the value of the current which is flowing through the circuit, the uh, intensity of the radiation can be approximated. Now for these vacuum type photocells, the anode and cathode is placed in an evacuated chamber, so there is nothing but vacuum inside the chamber. And for this sort of an phototube, it is normally connected in a very simple circuit like this, where the phototube is connected with a battery through a resistor, and there is also a microammeter in order to measure the amount of current flow. Now it has to be connected with a source or a supply, so that there is a potential difference between the anode and the cathode terminals, so that when there is an incident light which is causing some electrons to be ejected or emitted, so due to the presence of the potential difference between the anode and cathode, with respect for as a result of the applied supply voltage, the potential difference which will cause the electron to travel from one side to another. And for this type of phototubes, the current is amplitude or magnitude of the current is very low. So for that reason, an emitter which is in microampere range, or even if possible a lower range, that would be necessary to detect the change in current. So from that it can be suggested that this sort of design of vacuum type cells are less sensitive or have low sensitivity, because for a certain intensity of incident light it is producing very small amount of current. So for lower intensity lights it would be difficult to detect the change in the luminous flux. So in terms of the amount of current which is determined from the emitter, the intensity of light can be related to it directly, or the voltage drop which is taking place across this resistance R, that voltage can be also used to establish a relation between the intensity of light and the change in the voltage across the resistance R. Now, a particular IV characteristics curve for this sort of a photocell is shown over here, where in the x-axis there is the anode voltage, and corresponding to the change in anode voltage, what should be the change in the current flowing through anode to cathode is shown in this diagram. And the diagram is shown for uh, uh, light energy of different luminous flux. So for 0.2 lumen, then 0.4 lumen, in this way for different uh, luminous flux of the incident light, the characteristics graph is shown. Now there is a similar pattern for each of the curves for different intensity of the light, is that after a certain amount of voltage, uh, suppose after 40 to 50 volts, it is all the lines are getting saturated. So for a particular fixed amount of voltage or constant voltage, suppose if I draw a vertical line or consider a vertical line, so for a fixed amount of voltage, suppose 100 volts, if we only try to observe the relation between the change in luminous flux and the change in current, so it can be observed that it is quite it will give us quite a linear relationship, because from each I mean jump from one intensity to another intensity, the jump from in the value of the current is almost separated by equal amount. So in that sense it could be said that the relationship between the luminous flux and the anode current will have will show or exhibit a linear relationship. So for any particular uh, 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 constant voltage, when the voltage is not changing, if only the relationship between the light flux and the anode current is considered, a straight line can be obtained. So as it is related through a linear relationship, so whatever the change in current, that can be directly considered to be in proportion to the change in intensity. Now the current through the photocell, it depends on mainly the three parameters. The first one is the intensity of light, that is obviously uh, that is quite obvious actually. Then also the wavelength of the light, because the uh, energy of the photon energy produced by the light will depend on the wavelength, because you know that the photon energy is normally represented by this equation hc by lambda. So these two are constants, so you can definitely say that the energy produced by the photons will is inversely proportional to the wavelength. So depending upon the wavelength of the light, the photon energy will change, and uh, the corresponding energy will result in the emission of the electrons. So if the photon energy is not sufficient to uh, ionize the photoemissive material, then it will not be possible to generate free electrons. And if the photon energy is more than the required energy to ionize the photoemissive material, then electrons can be generated, which will be traveling from one side to another. Now, the voltage applied across the anode and cathode, that is also crucial, because sufficient amount of voltage difference has to be created between the anode and cathode, so that the uh, potential difference can drive the electrons from one side to another. Now, like one of the disadvantages of the vacuum type photocells were that they produce current of very low magnitudes in microampere range, or using those vacuum type phototubes, a sensitivity of 10 to 100 microampere per lumen can be obtained. So that is a very low amount of current. So for each change in the intensity of light of 1 lumen, it will cause very small amount of current deviation. So for very small intensity of light, this sort of a device will not be uh, giving accurate readings, because the small readings of the current might be difficult to detect using a particular device. Now, in order to increase the uh, accuracy or sensitivity of the vacuum type photo cells, a modified design was the gas filled photo cells. So in the structure is same as the vacuum type photocells. Only difference is that instead of vacuum, the enclosed chamber is filled with uh, an inert gas. So whenever there is an emitted electron from the cathode terminal, it will actually cause some ionization of the inert gas, which is inside the chamber. So if the emitted electron is kinetic energy is more than the ionization potential of that particular gas, then that molecules of that particular gas will separate into a positively charged ions and negatively charged electrons. So each particular emitted electrons from the cathode terminal in this process will generate further electrons by ionizing the gas which is present inside the chamber. So in this way, the number of electrons which is produced for a particular intensity of light can be increased. And if the number of electrons are increasing, then uh, the total amount of current flow is also likely to increase. So in this way, the sensitivity of the device can be increased as well. So by following this process, the gain of or response of the gas-filled phototubes can be increased from 5 to 10 times compared to the vacuum type phototubes. However, a slight disadvantage would be that whereas in case of vacuum type phototubes, the uh, relationship between the light intensity and the generated current was a linear relationship. Here the relationship will be having or it will tend to become non-linear for higher voltages. However, for applications which require a device of higher sensitivity, then this could be used as an alternative of the vacuum type phototubes. Now, a typical characteristics curve of the gas-filled phototubes are shown over here. Again, the anode voltage and the anode current is plotted, and for different intensity of light. So here it can be said that the graphs are not getting saturated after a certain amount of voltage, rather they are ever increasing. So that is actually going to cause the non-linear relationship between the intensity of light and the amount of current flow. Now, the last type of photoemissive cells or phototubes that I'm going to discuss is the photomultiplier tube, and it is actually designed in order to enhance the sensitivity even further. So for applications of which consist of low intensity of incident radiation, then this sort of photomultiplier tubes can be used, which will further enhance the sensitivity so that small changes in incident radiation can be detected. Okay, ID 81. ID 81, are you here? Are you here?
Hello, sir.
Yes. Did you raise
So,
hand?
sir,
Yes, I'm listening.
I have a question regarding gaseous phototube. You said that there is no saturation and the graph seems pretty smooth. And my question is that if the since it's gas, it should be temperature dependent. So, should there be any fluctuations in the graph because due to temperature, gas volume will change and the amount of electron may differ because of temperature?
Yeah, if there is too much temperature variations, then they might differ actually, because uh, for high temperature applications, even the temperature can play a significant role in the ionization of the gas. So that also plays a significant role, or that might impact the accuracy of that particular type of sensor, which is having an inert gas in its enclosed medium. So anything else you want to ask?
No, sir.
Okay, so photomultiplier tubes are a further modification of the previous two designs. So in this case, there is no inert gas inside the chamber. However, there are several other uh, uh, intermediate electrodes, we can say. Those are referred to as dinodes. And in this figure as well, in the general construction, it can be suggested that apart from the cathode and the anode, there are several other electrodes which are referred to as dinodes. Suppose dynode 1, dynode 2, dynode 3, in this way. So multiple stages of electrodes can be there. So the purpose of the electrodes is that of having several electrodes is that before the electron, which is initially emitted by the incident light from the cathode, before it reaches the anode, in each of the intermediate electrons, the focus is to generate further electrons in each stage. So if each of the electrodes are or dinodes are coated with photo sensitive materials as well, so whenever an electron is emitted from the cathode, it will be directed towards the first dynode, and uh, the energy contained by the electron will emit even further electrons from the dynode. So suppose this electron is coming over here, So it will get deflected and be directed towards the dynode 2, and in the process it might emit another electron from this particular electrode, which will again travel towards the second dynode. In this way, in this continuous process, in each stage in the intermediate electrodes, a higher number of electrons are supposed to be generated, which are later going to be collected towards the anode. So in this way, for the same intensity of light compared to the gas filled phototubes or the vacuum type phototube, the amount of light, amount of current can be increased because the total number of electrons are increasing. So
Sir,
yes,
sir, I didn't understand how the like electrons are multiplying when they hit the dynode.
so whenever a light energy is striking the cathode, so light is having some photon energy in terms of the I mean, depending on the wavelength of the light. So that photon energy is going to ionize the photoemissive material, and due to that an electron will be produced, suppose. So that electron is getting produced because the energy of the photon is getting transferred to the electron. So when the electron is now traveling from, and also there is a potential difference between dynode 1 and dynode and cathode, because the cathode is suppose connected to 0 volts and dynode 1 is connected to 100 volts, so there is a potential difference. So the electron will be directed towards dynode 1, and it is having some energy which it gained from the photon energy. So that kinetic energy, with that particular kinetic energy, the electron is now going to hit the surface of the dynode 1. So as it is I mean, having an interaction with this particular electrode, so obviously some energy is going to be exerted to this particular surface. So the material will now due to that exertion of the energy with which the electron is traveling into this into the presence of this potential difference. So that particular photoemissive material may also get energized, and it may convert into an ion and electron. So in this way, the energy which is contained by a particular electron which is emitted from the cathode, its energy can cause the material of the dynode 1 to ionize and produce even more electrons. So after hitting dynode 1, due to the concave surface, the electron is supposed to be deflected towards uh, dynode 2, and at the same time as it is exerting some extra electrons from this surface, and also there is further potential difference between dynode 1 and dynode 2, because again if you look, there is a potential difference of 100 volts here as well. So those electrons which are produced further, they are also going to start traveling towards the subsequent electrode. In this way, in this continuous process, when each electron is hitting the subsequent electrode, and due to the subsequent potential difference between each electrodes, the number of electrons which are generated are going to increase. And um, uh, when in this process, when they are finally reaching the anode, the total number of electrons which is initially produced, that is getting increased. So for vacuum type phototubes, let's say we only have this portion. Now these intermediate stages are causing the, in each stage as more electrons are getting produced, the overall number of electrons are getting multiplied, and finally they are connected towards the anode. So this will eventually result in the increase in the amount of current flow. So depending on the appropriate applied voltage at each diodes, 3 to 6 secondary electrons can be emitted for every primary electron which is striking the diode. So these secondary electrons then actually going to generate even more electrons from the subsequent diodes, and in this way the sensitivity of the device can be increased as the number of electrons are increasing.
Sir, another thing, sir. So
Yes.
does the potential of the diodes have anything to do with the number of extra electrons released for each primary electron?
Yes, if the voltage is higher, then that particular material is supposed to be more excited. So if it is more excited, or it then even a small amount of energy which it is getting from a traveling electron, that might be sufficient for producing even higher number of electrons.
Then,
However,
sir,
yes,
can't we use like fewer number of diodes with higher potential difference? Then the same thing should happen.
yeah, it can be done, but suppose uh, suppose if you are having two stages of suppose 0 to 100 volts, then 100 to 300 volts, or even the 700 volts, you are dividing into two parts. Now apart from the applied voltage, now when you are having smaller stages, and each stage you are creating large number of potential difference, that is supposed to enhance your uh, number of electron production. But along with that, if you can have multiple stages, then it might enhance your number of electron production even more, because suppose the dimension of the diodes can become a factor over here, because what is the dimension of the diode, depending upon that you can have some sensitive material. So even if there is higher voltage difference between them, it may increase the number of electrons up to a certain limit. Then after that, maybe it might get sort of saturated, that it cannot produce even more electrons for a particular instant. So in that sense, if you have multiple stages, that might be advantageous, but both of the things might have some pros and cons, and depending on a specific type of, or what is the need of a particular application, maybe a particular design is normally used.
Yes, sir. Got it.
Now, if some advantages and disadvantages are to be discussed, then uh, it can be said that as the photomultiplier tubes can detect lights or radiation with lower wavelength, then their frequency response will be comparatively higher compared to the other two types of phototubes. Now, the other thing is that the sensitivity of this sort of a device can be higher compared to the other phototubes as well. There must be a typo over here, so it should be 100 microampere. So using photomultiplier tubes, sensitivity of 20 amperes per lumen up to this might be obtained, whereas in case of other photomultiplier tubes, around 100 microampere per lumen is normally obtained. So compared to 100 microampere change in current in per change in per unit change in luminous flux. A 20 ampere change is more uh, easily detectable. So in that sense, the device is producing higher sensitivity compared to the other two designs. And depending upon the cathode material, the material photoemissive material which is used, the semiconductor material maybe that is used in the cathode. Depending upon that, the spectral response may vary. So it may vary from 100 nanometer to 1000 nanometer, and it may give you a wide range of operation limit wavelengths. So within this limit of spectral response, it is also covering the visible range of 400 to 700 nanometers. So for a wide range of wavelengths, it can be useful. And the disadvantages are the bulky design of this device, and due to the bulky design and also the requirement of generating high amount of voltages or voltage difference between multiple electrodes, so its cost is supposed to be higher as well, and the requirement of producing the high voltage and at each stage is also a disadvantage of this particular design. However, for their higher sensitivity or the high number of current that can be produced depending upon the change in intensity of light. So this amplifying capability can give some advantages, such as that there might not be necessary to use any other amplifier circuit in the subsequent portion of signal processing. And furthermore, for I mean applications which require accurate measurements, so photoelectric uh, for different photoelectric measurements and controlling purpose, this can be used, and for scintillation counters, this device can be used as well. So scintillation counters is actually a device which is normally used for approximating the amount of radiation. So uh, by light energy, it doesn't mean that the light energy is always going to come from the sunlight. Other than that, suppose if there is any radioactive material uh, in some nuclear reactor or nuclear reaction, so if that material is getting ionized, then it might create a charged ion electron, and at the same time it might produce some amount of light energy or photon. So if that photon is used to transfer into a photomultiplier tube, so from that uh, uh, I mean incident photon energy due to I mean ongoing radiation, how much current is produced from there, an approximation of the amount of radiation can be done using the photomultiplier with the help of photomultiplier tubes. Now let us start some discussion on photoconductive cells. Now for simple applications, the photoconductive cells actually replace the uses of photomultiplier tubes, because compared to the photoconductive cells, the designs of the photomultiplier tubes or the gas filled or vacuum filled phototubes are quite bulky and require higher voltage of operation. So compared to them, the photoconductive cells are relatively user friendly for small scale applications. So in photoconductive cells, you normally know this as LDRs or light dependent resistors. So where light sensitive material is present in this sort of devices, and in presence of the incident light or photon energy, the resistance of this particular device changes. So normally the material which is used, the light sensitive material which is used, it is the semiconductor material, and most of the semiconductor materials possess the characteristics of negative resistance. So which means that whenever there is going to be incident light, the amount of resistance is going to be decreasing. And uh, the advantage is that the decrease in the resistance will have a linear relationship with the intensity of incident light. So if I talk about the typical construction of an LDR or photoconductive cell, so it normally has a ceramic base, on top of which is the semiconductor material. A long strip of the semiconductor material is placed in a zigzag form so that a long strip can be accommodated into a smaller area, and after that that is enclosed into maybe a glass enclosure, so that moisture or other uh, uh, I mean from other corrosion it can be protected as much as possible. So typically the materials, semiconductor materials which are used are cadmium sulfide or germanium or silicon. So using these semiconductor materials, the LDRs can be uh, easily fabricated. And among these three, the cadmium sulfide is most commonly used because the spectral response that can be obtained while the cadmium sulfide is used, it is almost similar to the spectral response of the human eye. So for that reason, for automatic control of street lights or the automatic control of iris in a camera, for these purposes, the LDRs can be used, and they could be good alternatives of the photoemissive cells. And if the relation between the illumination of the light or luminous flux and the change in resistance of a particular LDR, it can be shown like this, which has a linear relationship. And also you can see that the resistance value is shown over here in kilo ohms. So which means that for per unit area, the light received in per unit area of a of an photoconductive cell, the change in resistance is significantly high. So if for per unit change in light intensity, the amount of variation in resistance is higher. So which means that for a small intensity of light, these devices can be used as well. However, like the other sensors as well, here the temperature will also become a factor, because the temperature, for temperature variation, the resistivity of the semiconductor material might change. So if the uh, uh, at the environment where the LDR is applied, used for a particular application, it might happen that due to higher temperature variations, the uh, value of the resistance might be affected in such a way that it is significantly high. So that could be one of the disadvantages. Now, lastly, today I want to finish the discussion on different types of photo transducers by photovoltaic cells, and later on in our next class we can start the discussion from photojunctions, which include photodiodes or phototransistors, and observe how they can be applied for certain applications. Now today, about photovoltaic cells, you are quite familiar with photovoltaic cells like the solar cells. So these are actually active transducers because they don't require external supply voltage, because you see the other optical transducers which has been discussed today. For operating them, external voltage is required so that the change in a particular quantity, suppose current or voltage, can be observed, or for providing the necessary excitation, uh, some external voltage or supply has to be uh, ensured. But in case of photovoltaic cells, you know that photovoltaic cells doesn't require any external supply. Rather, when there is incident light, it generates some voltage. So in that sense, they can be termed as active transducers. And from the amount of generated voltage, the change in the intensity of light can be predicted. So typically, you know, the construction of a photovoltaic cell consists of a p-n junction, that you have a p type material and an n type material, and using this when this p-n junction is exposed in incident light, then it is going to generate voltage as its output. Now the schematic diagram of the photovoltaic cell that is shown over here, its construction is slightly different. However, it is also a variation of the photovoltaic cell, where there is a semiconductor material, and there is a metal. So here also a junction will be formed, but it is not actually a p-n junction. So when there is a semiconductor material and it is having a junction with a metal, do you guys remember the name of the junction? What that junction is normally called when you merge a semiconductor material with a particular metal? So when a semiconductor and a metal is merged together, then the junction which is formed, it is normally called the Schottky junction. So this particular figure is actually representing a Schottky junction solar cell, but usually normally the p-n junction solar cells are widely used, but the Schottky junction solar cells could be good alternatives of p-n junction solar cells if uh, the cost of fabrication is an issue, because they can be, the Schottky junction solar cells can be fabricated at a lower cost, and uh, the barrier potential normally that is present in the depletion region is also high in case of Schottky junction. So considering the higher barrier potential and the lower value of cost in production, they can be sometimes used as the alternative of the p-n junction uh, photovoltaic cells. Now, in the previous class of section A, when the capacitive transducers were discussed, a small portion was not covered, so which was actually later on discussed in section B. Now, as both the sections are have joined here today in this session, now the portion of the discussion regarding the differential arrangement of capacitive transducers, that has been already discussed in section B. So for section A, I'm just going to repeat it. So if the students of section B, as it is already covered in the previous class, they can leave the meeting, or they can stay. That depends up to them. But for section A, I am repeating this portion as it was not covered in their previous class. So in previous class, we studied up to how depending upon which variation of which parameters that different capacitive transducers can be formed. So here in this portion of the discussion, I'm going to discuss about the differential arrangements that can be uh, formed in case of capacitive transducers, like in case of LVDT or RVDT, the linear variable differential transformer or rotary variable differential transformer, which were discussed in the previous class, which were of inductive type of differential transducers. There, if you remember, the output voltage was in the form of differential voltage. So we were taking voltage difference between two inductive coils on the secondary side. So similarly, by having differential arrangement of capacitive transducers, we can also take the output as the difference between two voltages between two capacitors. So if we can form a differential arrangement where we have two varying capacitors, and if, with respect to the variation in the values of the two capacitors, finally the output can be taken with respect to the voltage difference between the two capacitors. Now the differential arrangement can be uh, uh, obtained also through following the principle of varying the area of overlap, or changing the distance between the plates, or changing the dielectricity between the plates. So our goal is to have two capacitance which will vary with respect to the change in the physical quantity. So in order to have two uh, variable capacitance, one arrangement could be like this, which is shown over here with respect to the change in overlapping area. So here the two bottom plates are static plates, whereas the upper plate is a movable plate which can move along the horizontal uh, direction. So if it is located at the middle in such a way that both the lower plates are having equal share of the overlapping area with the upper plate, then the two capacitances produced between the upper plate and the two lower plates are going to be equal. Suppose if the capacitance between the upper plate and the first lower plate is C1, and between the upper plate and the second lower plate is C2. So at the null position, both the capacitances C1 and C2 is going to be equal. However, if the upper plate is moving either on the right hand side or the left hand side, depending upon the overlapping area, the two capacitances C1 and C2 are supposed to be changing. So if some external voltage is applied across this differential arrangement, then the voltage drop across the two capacitors will also change, and eventually the difference between the two voltages across the capacitors can be taken as the differential output, and the output can be taken in the form of an AC bridge circuit. So if this particular differential arrangement of the capacitive transducer is connected in the form of an AC bridge, so the capacitances C1 and C2 and the two resistances, suppose R1 and R2, they are forming the four arms of the AC bridge, and the equivalent schematic diagram can be shown over here, where this is C1, the capacitance between the upper plate and one of the fixed plates, and this is C2 with the upper capacitance between the upper plate and the other fixed plate. So depending upon the change in the direction of movement of the upper plate, the C1 and C2 is going to be varied, and if the volt output is taken from these two nodes in terms of a voltmeter, then that voltmeter is actually going to give the differential voltage between the capacitor C1 and C2. So with respect to that differential voltage, how much displacement has taken place, that can be approximated. Similarly, another differential arrangement of capacitive transducer can be obtained by uh, the principle of varying distance between the plates. So in figure B, there are three plates connected one after another. For this type of arrangement, the upper plate and the lower plate is considered to be fixed, and the middle plate is considered to be the movable plate. So it can move along the vertical line, and if it is moved upwards, then the distance between the upper plate and the moving plate will decrease, and the distance between the moving plate and the lower plate will increase. So in this way, whether it is moving upwards or downwards, the two capacitances, suppose C1 and C2, will change. Similarly, the differential arrangement, one differential arrangement can also be obtained by varying the dielectric material between the plates. So for this sort of arrangement, all the three plates, the upper plate and the two lower plates, can be considered to be static, and depending on the movement of the dielectric material, the presence of the dielectric material, or how much dielectric material is present between the two plates, that might change the values of the capacitances. So in this way, following the three principles, the differential arrangement of capacitance can be obtained, and finally the output can be taken as the difference between voltages using a bridge circuit. Now, for a particular type of differential arrangement, which is that obtained through the change in distance between the plates, the expression for the differential voltage can be obtained. So in terms of the displacement x, suppose x is the displacement of the movable plate. So in terms of the displacement x, the change in differential voltage can be an expression of that can be obtained. So first of all, let us consider that the upper plate and the lower plate are the two fixed plates, whereas the movable plate is located in between them. So if it is placed right at the middle, then the distance between both the fixed plates and the movable plate is equal. So the capacitance C1 and C2 between the upper plate and the movable plate, and the lower plate and the movable plate respectively, are going to be equal, as the distance is same. So as a result, the voltage drop, if these two plates are suppose connected to a supply voltage, the upper and the lower plate, which are the fixed plates, then depending upon the position of the movable plate, the voltage across both the capacitors C1 and C2 will also change. So similar to what we do for a resistive circuit, we can sort of apply the voltage divider rule in the form of capacitive reactance, and obtain these two expressions for the voltage drop across C1 and C2. So here, as we are considering both the capacitances to be equal, so later on by cancelling the terms, we can find that the voltage will be equally divided between the two capacitors, and the differential output is going to be 0 when the movable plate is located just at the center. Now, if the movable plate is now moving upwards or downwards, the distance is not going to be same as before or same as the null position. So if it is moving upwards by a distance x, then the distance between the upper plate and the movable plate will be d minus x, whereas the distance between the lower plate and the movable plate will be d plus x. So with respect to that, we can rewrite the expression of the capacitances, and if we use the same expressions for calculating the voltage drop across the two capacitors and put the expression of C1 and C2, finally we'll see that the expression of E1 will be this one and the expression of E2 will be this one. And if we take the difference between E2 minus E1, then finally we will end up with this expression. So here E and D can be considered to be fixed for a particular set of arrangement, because the distance between the upper plate and the lower plate, which are fixed plates, that distance is not changing. So D will be half of that distance, so it can be considered to be fixed. The supply voltage can be also considered to be fixed for a fixed amount of supply voltage. So in this way, the change in differential output can be related to the change in displacement of the movable plate. And also from here, the sensitivity of this sort of an arrangement can be written. So the sensitivity will be the change in differential voltage with respect to the change in displacement. So that can be the uh, that can indicate the sensitivity of this sort of a differential arrangement. And in place of delta E, if this expression is used, then E by D will give a measure of the sensitivity of this sort of an arrangement. So this was the discussion on differential arrangement of capacitive transducers. Now in the later slides, there are some advantages and disadvantages and some applications of capacitive transducers given on the slide. Now I hope that you can go through these slides because they are quite straightforward, and I think if you read by yourself, it will be sufficient. And if you have any question regarding the overall discussion done today, you can ask. Otherwise, I can conclude today's session. Okay, so maybe you're not going to ask anything. So about Saturday's quiz, I'll try to provide you the links of the Google form in your respective Google classes in the Google Classroom. So you should access the form up from there, and you have to access them using your email address, which is provided by IUT. And what will be the time limit? I will mention beforehand. Maybe tomorrow or Saturday morning, I'll specify the time limit. So within that time limit, you have to submit your responses, and after that time limit, I will not be accepting any late submissions. So that's it for today.
So
And
what will be the question pattern like?
the question pattern would be MCQ based. So there would be mostly multiple choice questions. There could be some short questions as well, where you have to type in something. Maybe if there is some small mathematical problems given, you might have to type in the answer. Or even if some mathematical problems are given, then you might have, if that is a multiple choice type question, you might have to select the correct answer from the different options. So if some information is necessary to type in, so you can type in the text boxes. Otherwise it will be mostly multiple choice type, and for each question there could be one or multiple correct answers. So depending upon that, you have to uh, uh, give your answers. So the syllabus I have already mentioned before. I mean, I informed the seers as well, and I think I also mentioned in the previous class. It would be up to the different techniques of uh, uh, measuring high resistance starting from the beginning. So before, what was discussed before the discussion of AC bridge circuits. So in your Google Classroom, you will see that I have highlighted the articles and some example problems regarding the different topics. So you can go through those, and uh, uh, there will not be any derivation, as this is a multiple choice question, but you should also go through the derivations, because if there is some questions regarding any intermediate stage of the derivation, so that you can answer that. And regarding the mathematical problems, some problems, example problems have been highlighted in your Google Classroom regarding the DC bridge circuits. Then uh, for chapter uh, for different types of error, uh, you can refer to chapter 2 of David Abel. You can go through that and go through the example problems as well to have a better idea, and also try to follow the lectures. Maybe some things which is not directly given in the book, but in one way or another was discussed in the lectures, that might also come in your exam. So any other questions regarding the exam?
So AC bridge circuits is not included, right?
No, it is not included. Whatever was discussed before that, up to that is included.
Okay.
Okay, best of luck everyone. I think it will be a very easy quiz, and hope you will be able to answer all the questions.